So if we look back at the summer of 2016, there was this massive warehouse fire in the U.S. They were storing industrial solvents.
Right, a really catastrophic one.
Yeah, exactly. And by the time the first fire engines even got to the scene, the whole thing had just escalated. I mean, it was way past a manageable structural fire. It was an absolute industrial inferno.
Yeah, totally out of control.
Right. And the heat was so intense, it was literally warping the steel support beams of the facility. The environmental fallout took months to even figure out. But, and this is the crazy part, when investigators finally dug through the ashes, the root cause was so frustrating.
Because it wasn't some complex chemical anomaly.
No, not at all. It wasn't an exotic reaction. It wasn't arson. The primary reason the whole place was a total loss was just geometry. The storage tanks were simply positioned too close together.
Yeah.
Like proper spacing, which is a basic calculation dictated by the National Fire Protection Association, could have stopped a localized leak from turning into a multi-million-dollar disaster.
It's a really sobering case study, honestly. And it highlights something that, anyone working in industrial safety eventually has to face.
Which is what, exactly?
Well, we tend to treat safety as just buying the right gear, right? Like, oh, we have the right pumps, we have the loudest alarms, we're good.
Right, the hardware.
Exactly.
Yeah.
But when you're dealing with highly volatile materials, safety is actually an architectural and spatial discipline.
A spatial discipline. I like that phrasing.
Yeah, I mean, that 2016 fire, that was fundamentally a failure of spatial risk management. If you don't respect the invisible vapor boundaries and the radiant heat zones, you just surrender control of the environment the second a spark happens.
Which perfectly sets up our mission for today's deep dive. If you are a fire protection engineer sketching out a new layout right now, or maybe you're a safety compliance officer evaluating a plant floor.
Or even if you're just fascinated by industrial safety.
Exactly. If you just love knowing how the modern world doesn't spontaneously combust every day, this is for you. We are taking a comprehensive look at NFPA 30, specifically the 2021 edition of the Flammable and Combustible Liquids Code.
And our main goal here is to really cut through the dense regulatory language, because NFPA 30 is a consensus standard.
Right, meaning everyone in the industry kind of hammered it out together.
Exactly. It's the collective hard-won knowledge of the industry.
Yeah.
But, reading it can feel like wading through this endless sea of dry tables and footnotes.
It can be a tough read.
It really can. So we want to pull out the actual thermodynamic principles behind those tables, because you're not just checking boxes for a fire marshal.
No, you're dictating the physics of how a disaster will or won't unfold in your building.
Precisely.
So let's start with this massive paradigm shift in the 2021 edition, because for the longest time, engineers divided these hazards into two really distinct buckets, right? Flammable liquids and combustible liquids.
Right. Those are the entrenched categories for decades.
Yeah, and you'd see those two words stamped on every barrel, every safety data sheet, every placard. But the 2021 code just aggressively stripped those terms out, like entirely.
It was a huge change.
Right, and they replaced them with just one overarching umbrella term, ignitable liquid.
And the history behind why they did that is actually really fascinating, because it wasn't some sudden breakthrough in chemistry.
Right, it was bureaucracy, wasn't it?
Yeah, it was bureaucratic friction creating actual physical danger on the ground. For years, we had this fractured regulatory landscape.
Like different agencies having different rules.
Exactly. You had OSHA, the Occupational Safety and Health Administration, governing the worker on the factory floor.
Okay.
Then you had the DOT, the Department of Transportation, governing how that chemical gets moved down the highway.
Right.
And then you had local fire marshals using early NFPA standards for building codes.
Okay, I see where this is going. If I'm a facility manager and I move a 55-gallon drum of, say, methyl ethyl ketone off my floor onto the dock and onto a truck,
you are crossing 3 different regulatory domains in about 100 yards.
it sounds like a nightmare.
It was. And historically, those 3 domains used slightly different temperature thresholds to define what was flammable versus combustible.
Oh, wow. So OSHA might say it's combustible.
Right, allowing certain handling, but the DOT might look at the exact same drum and say, no, that's flammable.
Which means totally different placards and emergency protocols.
Exactly. And that created massive compliance gaps. And in this industry, a compliance gap eventually turns into a casualty.
So the NFPA just stepped in and said, enough.
Basically, yeah. They said, let's ignore the subjective adjectives. We're just going to look at the closed cup flash point. If it flashes, it's an ignitable liquid. The hazard is based on objective thermodynamics now, not a legacy label.
So it's like we used to argue about whether a pepper was spicy or hot based on who was eating it.
That's a great analogy.
Right. But now we just use the Scoville scale. So everyone is on the exact same page, regardless of what kitchen they work in.
Exactly. It's a universal baseline.
Now, you mentioned closed cup flashpoint, and I want to pause there because engineers see that on safety sheets all the time. But the physical mechanism is so important. A lot of people probably assume you just hold a lighter over a puddle of liquid and see if it catches fire.
Right, which would be an open cup test, essentially.
But the closed cup method is way more precise, isn't it?
It is entirely different. In an open cup test, the liquid is heated while exposed to the ambient air, so any vapors it makes can just drift away into the room.
Which means you might get a falsely high reading of when it actually becomes dangerous.
Exactly. But the closed cup test, like the Penske Martins or the Tagliabue closed tester, you put the liquid in this sealed brass cup,
Okay.
and then you slowly, meticulously heat it up, maybe a couple of degrees a minute. And because it's sealed, those vapors get trapped in the tiny void space right above the liquid.
So it creates a really concentrated vapor-air mixture,
Right.
which perfectly mimics the worst-case scenario, like a steel drum baking in the sun inside some unair-conditioned warehouse.
That is exactly the point. It simulates confined hazard conditions. So at specific intervals, there's this tiny mechanical shutter on the lid that pops open for just a fraction of a second.
And they dip a flame in.
Exactly. A test flame drops into that trapped vapor space. And the flash point is the exact absolute lowest temperature where there's enough concentrated vapor to cause a distinct flash of ignition across the surface.
Okay, so that universal Scoville scale is established. Let's look at the classification matrix in Chapter 4 because it meticulously subdivides these ignitable liquids based on that flash point, which we'll call FP, and the boiling point, or BP.
Right.
Let's start with the absolute scariest end of the spectrum. Class I liquids. These are liquids with a closed cup flash point below 100 degrees Fahrenheit, or about 37.8 Celsius.
And I'd argue that 100-degree Fahrenheit mark is the most critical dividing line in the entire code.
Really? Why 100 degrees?
Because it represents a standard, achievable ambient temperature. If a liquid flashes below 100 degrees, it means that on a warm summer day, just sitting there in its natural environment, it has enough thermal energy to generate a highly explosive vapor layer.
You don't even need a heater or a fire. The weather is enough.
Exactly. The weather does the work for you.
That's terrifying. And within that dangerous Class I family, the code breaks it down into IA, IB, and IC. So Class IA is the absolute most volatile, flash point below 73 degrees Fahrenheit, so basically room temperature, and a boiling point below 100 degrees.
Yeah, a liquid with a boiling point below 100 degrees really doesn't want to be a liquid at all.
It just wants to be a gas.
Right. Under normal atmospheric pressure, it's desperately trying to phase change. It takes almost zero energy to force it to boil and rapidly off gas. These are usually highly specialized chemical feedstocks.
Okay, then we have Class IB. Flash point is still below 73 degrees, so it's off-gassing at room temperature, but the boiling point is at or above 100.
Slightly more stable against rapid boiling than IA, but still incredibly dangerous.
And finally, Class IC. Flash point is at or above 73, but strictly below that 100-degree mark.
And Class IC is insidious because it behaves totally differently depending on the season.
Right, because of ambient temperature.
Exactly. On a cool November morning, a spill of a Class IC liquid might not immediately create an explosive cloud, but if that exact same spill happens on a hot July afternoon in a poorly ventilated metal warehouse...
It's actively pumping out an ignitable vapor blanket.
Right. It really demands situational awareness from the operators.
Okay, so that covers the Class I family flashing below 100 degrees. What about the rest? The legacy combustible liquids, which are now Classes 2 and 3.
So these are your liquids with the flash point at or above 100 degrees Fahrenheit. Class 2 is from 100 up to, but not including, 140 degrees.
Yeah.
Class IA is 140 up to 200 degrees. And Class IB catches everything 200 degrees and above. Think heavy lubricating oils, motor oils, hydraulic fluids.
So a Class IB liquid needs a ton of thermal energy to off-gas enough to ignite. I feel like you could almost drop a lit match into a bucket of some IB liquids at room temp and it would just put the match out.
You likely could, actually.
Really?
Yeah, but that high flash point often lulls people into a false sense of security. Make no mistake, once a Class IB liquid is heated past that 200-degree mark, say, by a smaller trash fire nearby.
Becomes a massive fuel load.
Massive. It will burn with immense sustained energy. The key takeaway for you, the engineer listening, is that this classification matrix drives literally every single design constraint in your building.
You're never just designing a generic liquid storage room.
Never. You're designing a space specifically calibrated to the vapor dynamics of a Class IB or a Class IA liquid. It dictates your electrical zoning, like whether you need explosion-proof light switches. It dictates mechanical ventilation. It dictates spill containment.
And, we actually have a true story from our sources that perfectly illustrates what happens when you treat all liquids like they have the same risk profile.
Oh, the factory incident, yes.
Yeah, so there was this manufacturing factory, and they were storing highly volatile Class I solvents and relatively stable Class II oils right next to each other in the exact same general warehouse space.
They didn't establish distinct hazard zoning.
Right. The building's ventilation and electrical systems were basically engineered for the baseline hazard of the Class II oils.
Which is a classic fatal compounding error. You have a room engineered for a liquid that only off-gases at 120 degrees.
Exactly. And then, naturally, a minor leak happens from one of the Class I containers. Since it flashes at room temperature, it instantly starts generating this dense vapor cloud.
And the baseline ventilation just couldn't clear it.
No chance. The vapor rapidly accumulated in a low-lying pocket of the warehouse, and then an ignition source, reportedly just a standard spark from a forklift.
Which would have been totally fine around the Class II oils.
Right. But it found that invisible Class I vapor trail. The ignition flashed back to the source, rapidly heated the nearby Class II drums past their flash points, and the entire shared storage area just went up. A total loss.
It's a grim story, but it absolutely validates the code's strict separation rules.
Yeah.
You cannot commingle a liquid flashing at 70 degrees with one flashing at 150 without designing the entire space to the most severe hazard.
Class separation literally saves lives.
It really does.
Okay, so we know the chemistry, we know the vapor dynamics. The next step for a facility engineer is containment geometry. How do we legally put these liquids inside a building? Which brings us to MAQs, or maximum allowable quantities.
Right, Chapter 9. This is where we shift from physical chemistry to architectural geometry. Table 9.6.1 is essentially the Rosetta Stone for facility planners.
And if you look at the baseline numbers in that table, they are shockingly low if you don't have active fire protection. Like for Class IA, the most volatile, if you want to store it in a standard unsprinklered building, your legal limit is 30 gallons.
30 gallons. To put that in perspective, a standard industrial steel drum is 55 gallons.
So you can't even have one full drum.
Nope. The code is basically telling you that one full drum of Class IA in an unprotected space fundamentally violates the safety envelope of the entire building.
Why 30 gallons, though?
Yeah.
What's the math behind that specific number?
It's all about potential energy yield. If 30 gallons of a Class IA liquid were to spill and completely vaporize,
Which it wants to do at room temp.
right, that resulting vapor-air explosion has enough force to literally blow out the structural walls of a standard-sized commercial room.
Oh, wow.
Yeah. 30 gallons is the calculated threshold where the energy release surpasses standard structural resistance. Now, for Class IB and IC, because their boiling and flash points are slightly higher, that unsprinklered limit bumps up to 120 gallons.
But 120 gallons is still just about 2 drums. If I'm running a pharmaceutical compounding facility, I need way more than 2 drums to stay operational. How do I legally get more volume?
You buy it with engineered safety hardware.
Okay, explain that.
The code introduces control areas, which are fire-rated compartments. But the big one is sprinklers. If you install an NFPA 13-compliant automatic sprinkler system, the code instantly gives you a 100% increase in those allowable limits.
Because the rapid cooling mitigates the structural failure risk.
Exactly. So your 30 gallons becomes 60, your 120 becomes 240, and these allowances actually stack.
Wait, they stack.
Yeah. If you mandate that those liquids are kept inside approved liquid storage cabinets, you get another 100% increase. So by layering sprinklers and thermal cabinets, you exponentially increase your operational capacity safely.
Let's talk about those cabinets, actually.
Yeah.
Because Section 9.5 spells out the requirements. And this isn't just a gym locker you buy at a hardware store. It's highly specific passive fire protection.
It's a localized bunker. The code says the bottom, top, doors, and sides have to be at least 18-gauge sheet steel.
Which is pretty thick, like a 20th of an inch.
Right, but the thickness isn't even the main defense. The cabinet must be double-walled, with a mandatory 1.5-inch continuous airspace between the inner and outer steel skins.
The thermodynamics of that air gap are so cool. We always think of insulation as dense stuff, like fiberglass.
Hmm.
But static air is a terrible conductor of heat, which makes it an amazing insulator.
It's the thermos principle. If an external warehouse fire happens, the outer steel skin absorbs that massive radiant heat. But the heat really struggles to cross that 1.5-inch air gap via conduction.
So it slows down the temperature rise inside the cabinet.
Exactly. It buys you time. It prevents the internal temperature from reaching the boiling points of the solvents inside, which would cause the containers to burst and add fuel to the main fire.
The code also says the joints have to be riveted, welded, or thermally tight. You can't just use screws, right? Because they'd warp and pull out in a fire.
Right, compromising the air gap.
And there's this detail about the base. The door sill has to be raised at least 2 inches above the bottom inner surface.
That's a built-in dite. If someone drops a glass bottle of reagent, that 2-inch sill keeps the liquid entirely contained inside the cabinet footprint.
So it doesn't creep out under the door and find a spark 50 feet away?
Precisely. Also, the door has to have a robust 3-point latch. In a 1,500-degree fire, the steel will warp violently. A single latch would just pop right open. The 3-point latch holds it tight against the frame.
Now, speaking of holding it tight, there's a totally counterintuitive rule in the text here. If I'm a safety officer looking at a sealed metal box of explosive chemicals, my first thought is, we need to ventilate this box so fumes don't build up.
Naturally.
But the code explicitly says storage cabinets are not required to be ventilated for fire protection. In fact, if you do ventilate them, you have to run highly specific fire-rated piping all the way outdoors.
Yeah.
Why does NFPA discourage venting a box of fumes?
It feels wrong, I know. But you have to view the cabinet through the lens of a fire scenario, not just daily operations. Its only functional purpose in an emergency is to be an unbroken thermal envelope.
Yeah.
If you drill a hole in the top and bottom for a standard vent, you just compromise the envelope. You made a pathway for fire to enter.
Because if the vent duct isn't fire-rated, it just melts away.
Right.
And you've installed a chimney on your fuel source.
Exactly. The intense updraft of a warehouse fire will literally suck the flames right through those vent holes and into the cabinet, instantly boiling the contents.
Wow.
And conversely, if a small ignition happens inside the cabinet, standard ventilation provides a continuous draft of fresh atmospheric oxygen, letting the fire rapidly consume everything inside.
But if it's sealed?
If it's sealed and unventilated, you restrict the oxygen. Any internal fire will quickly burn up the limited oxygen in the box and literally choke itself out.
The NFPA prefers a concentrated, contained box of vapors over a ventilated box that breaches the firewall.
That's the engineering philosophy in a nutshell.
And managing vapor through proper zoning is so critical.
Yeah.
We have another true story from the sources here. There was a devastating explosion at a chemical manufacturing plant in India.
Right, a really tragic event.
When forensic engineers rebuilt the sequence of events, it wasn't an equipment failure. The ignition was traced directly back to poor ventilation design around their larger operational storage tanks.
Yeah, the HVAC systems just weren't providing enough air turnover in the low-lying areas.
Because ignitable vapors are almost universally heavier than air, right? They don't float up like steam.
They behave exactly like water. They pour over the edges of a tank, they sink to the floor, and they pool in trenches, drains, and corners.
And that's exactly what happened in India. This massive, invisible lake of highly explosive vapor just pooled in a stagnant pocket of the plant because the airflow was inadequate. A stray spark from routine maintenance happening well away from the actual tanks found the edge of that vapor pool.
And the explosion propagated instantly back to the source.
Total devastation. They had to completely rebuild the facility. And the redesign relied heavily on the mechanical ventilation standards in Chapters 10 and 17 of NFPA 30 to ensure continuous swept airflow across all those pooling areas.
It's a stark reminder. You have to engineer your airflow, assuming the vapor is already there, just actively seeking a way out.
Okay, so we've covered passive defense, cabinets, MEQs, airflow. But what happens when the worst-case scenario unfolds? A forklift breaches a rack of drums, a spark finds the vapor, and passive containment fails.
Now we transition to active defense.
Exactly. The engineer's toolkit for active suppression. This is Chapter 16, which covers automatic fire protection for inside liquid storage areas. It is easily the most mathematically dense section of the code.
It really is. And the foundational decision an engineer makes here is picking the right suppression medium, namely automatic water sprinklers versus low-expansion foam water systems.
Hey, just to be clear for you listening, when we say water sprinklers for industrial liquid storage, we are not talking about those little recessed heads in your office ceiling.
Oh, absolutely not.
The code demands massive density requirements based on the liquid class, the container type, rack height. I'm seeing design tables requiring delivery densities ranging from 0.21 gallons per minute per square foot all the way up to an astonishing 0.60 GPM per square foot.
To contextualize, 0.60 GPM per square foot. That is a torrential, localized monsoon.
Right.
It requires massive fire pumps, huge piping diameters, and an enormous municipal water supply. It's a highly aggressive tactic to rapidly cool the ambient temperature in the steel containers so they don't boil.
But, and here's the crucial caveat, when you're dealing with massive volumes of ignitable liquids, dumping thousands of gallons of water is sometimes the absolute worst thing you can possibly do.
Yes, it comes down to the chemical interaction between the solvent and the water. Specifically, is the liquid miscible or non-miscible?
I see this trip people up in safety training all the time. Miscible liquids like high-proof alcohols or certain polar solvents mix readily with water.
Right, the water actually dilutes the fuel, eventually bringing it below the flammability point.
But non-miscible liquids, your massive family of hydrocarbons, gasoline, diesel, heavy oils, they do not mix with water. And crucially, they're less dense than water.
Which means if you have a massive pool fire of a non-miscible hydrocarbon spreading across your warehouse floor, and your suppression system drops 0.60 GPM of pure water on it.
The burning fuel just floats on top of the rapidly accumulating water.
Exactly.
You essentially build a boat for the fire. The sprinkler system creates a rushing current of water that carries this burning hydrocarbon right out the loading dock doors, down the drainage trenches, and spreads the fire into totally new sections of the building. You create a flaming river.
And that is precisely when low-expansion foam water sprinkler systems become mandatory. Instead of just cooling and diluting, foam uses advanced fluid mechanics.
How does that work mechanically?
The system injects a specialized synthetic foam concentrate, usually an aqueous film-forming foam, or AFFF, into the water piping before it hits the sprinkle head. When that pressurized mix hits the air at the nozzle, it aggressively expands into a thick, aerated blanket.
The mechanics of that blanket are brilliant. It attacks the fire on three fronts. First, the water in the foam provides cooling. Second, the physical mass of the foam acts as a barrier, floating on the hydrocarbon and cutting off the atmospheric oxygen.
And the third front is vapor suppression, which is probably the most vital.
Right.
The aqueous film actually seals the surface of the liquid, physically preventing more ignitable vapors from off-gassing and feeding the thermal column. By choking off the vapor, you choke off the fire.
We have a great real-world example of this from our sources. A massive European refinery had a critical incident in a dense tank farm storing Class 3A liquids. A mechanical failure sparked a fire that rapidly engulfed a containment area.
Normally, a fire in a packed tank farm creates a domino effect. Adjacent tanks heat up until they fail.
Exactly. But this facility had invested in a state-of-the-art low-expansion foam system, engineered for that exact square footage and hazard class.
And it deployed flawlessly.
Within minutes, the aerated blanket completely covered the dike, suppressed the vapor, and smothered the flames before radiant heat could compromise the other tanks. A potential total loss was contained to a single incident. The engineering did exactly what the physics dictated.
It's a perfect success story for foam, but Chapter 16 introduces another variable that engineers have to account for, and if you don't understand the thermodynamics, it completely upends common sense.
Okay, let's get into this. This is about the physical design of the containers themselves.
Right. We need to explore the terrifying distinction between relieving containers and non-relieving containers.
This relies heavily on empirical test data detailed in Annex E of the code. So, a non-relieving container is exactly what it sounds like. A rigid, hermetically sealed vessel, like your standard, heavy-duty 55-gallon steel drum.
And a relieving container is designed to lose its structural integrity under heat.
Like a large plastic intermediate bulk container, an IBC that just melts.
Exactly. Or a steel drum fitted with specialized plastic or fusible metal plugs that melt and pop out when the temperature spikes.
Now, if I am a layperson, and I'm staring at a warehouse full of explosive chemicals, my intuition screams that those chemicals need to stay tightly locked inside an impenetrable steel vault. I want the non-relieving steel drum because it looks tough.
It looks safe.
Right. But the test data in Annex E reveals a catastrophic flaw in that logic. When a sealed, non-relieving steel drum is exposed to an external fire, the liquid inside acts like a heat sink.
It absorbs thermal energy straight through the steel shell.
And the liquid starts to rapidly boil, turning into a gas. Because the drum is sealed, that expanding gas has nowhere to go. The internal pressure starts climbing exponentially.
And steel drums are not high-pressure vessels. They are built to hold the static downward physical weight of the liquid, not immense outward pneumatic force.
Right.
According to the fire testing protocols in the annex, a gauge pressure of just 15 psi is identified as a critical threshold where violent structural failure can begin.
Wait, 15 psi. To contextualize that for you listening, you inflate your car tires to like 35 or 40 psi. 15 sounds completely negligible.
It sounds low, but pressure is force over area. When you apply 15 pounds of outward force to every single square inch of the huge internal surface area of a 55-gallon drum.
You're generating thousands of pounds of total outward stress.
Exactly. Now, the code notes many drums can technically hold up to 44 psi before failing. But the failure mode in a fire is not a slow, polite leak.
No, it is a dynamic, catastrophic rupture. The hoop stress overcomes the tensile strength of the steel, usually the seam where the lid is crimped to the shell.
And when that seam yields, the drum rapidly depressurizes.
All that superheated liquid inside instantly flash boils, expanding its volume exponentially in a fraction of a second.
This is what the industry calls a BLEV, a boiling liquid expanding vapor explosion.
The physical results of a BLEV are just staggering. The structural failure of that seam essentially turns a massive steel drum into an unguided rocket.
It really does.
The bottom blows out, and the main body of the drum launches across the warehouse, trailing a huge concussive fireball.
Ugh.
A flying steel drum weighing hundreds of pounds will easily shear right through structural support columns,
And shatter the overhead sprinkler piping.
instantly blinding the facility's primary fire defense system.
You lose your suppression capabilities at the exact moment the fire load increases tenfold. It is an entirely unrecoverable scenario.
Which leads to this brilliant, counterintuitive piece of engineering deduction. As a fire protection engineer, reviewing the devastation of a non-relieving steel drum, BLEV, I have to make a calculated choice. I realize I actually want my container to fail early.
Yes.
I want the plastic IBC to melt into a puddle at 300 degrees. I want the fusible plugs on my metal drums to pop out and actively spill their highly flammable contents directly into the fire.
It's a profound realization, isn't it? You are intentionally opting to feed the fire.
But the logic is impeccable. A plastic container that melts releases its liquid onto the floor, making a large, spreading pool fire. But a pool fire is a two-dimensional, predictable engineering problem.
We know exactly how a pool fire behaves.
We can build physical dikes and drainage trenches to dictate exactly where that burning liquid flows. We can calculate the exact density of low-expansion foam needed to smother a two-dimensional surface area.
But a rocket-propelled steel drum destroying your ceiling infrastructure, that is a chaotic, three-dimensional catastrophe.
You cannot engineer a sprinkler system that survives an artillery strike.
Exactly. By using relieving containers, the engineer is actively dictating the terms of the failure. You accept a massive pool fire because you can manage it rather than risking a BLEV, which you cannot survive.
And this choice directly impacts the design tables in Chapter 16. The code severely penalizes the use of non-relieving containers. If you insist on using sealed steel drums, your maximum allowable storage heights are drastically restricted, and your required water density is pushed to the absolute limits of your pumps.
The code essentially forces the engineer to respect the physics of pressure.
Okay, so we've covered the microscopic volatility metrics, indoor containment architecture, and the violent thermodynamics of drums. Now we need to step outside the warehouse. We need to shift to the macroscopic view.
Chapter 22. Storage of ignitable liquids in tanks.
Right. We are leaving the 55-gallon drums behind and entering the massive scale of the refinery yard, above-ground storage tanks, or ASTs.
The scale here alters the geometry of safety entirely. These are custom-built steel vessels holding hundreds of thousands, sometimes millions of gallons of highly volatile hydrocarbons.
At that volume, indoor control areas and sprinkler heads are totally irrelevant.
Completely. Your primary defense mechanism is raw geographic distance.
I'm looking at Table 22.4.14 BB. It dictates the required separation distances between these massive tanks, property lines, and important buildings. If a refinery has a tank over 100,000 gallons, the spacing requirements push out to immense distances.
Because the code is calculating radiant heat flux. If a 100,000-gallon tank of crude oil ignites, the thermal column generates a radiant heat footprint so intense it can easily ignite the roof of a building hundreds of feet away.
Or cause a neighboring tank's steel shell to buckle.
Exactly. The code mandates vast clear zones, so a single tank fire cannot geometrically bridge the gap to the rest of the facility.
But the spacing isn't uniform. The code allows tighter grouping depending on the physical engineering of the tank itself, specifically differentiating between fixed roof tanks and floating roof tanks.
Right.
If you've driven past a coastal refinery, you've seen these. A fixed roof tank is visually straightforward, a massive cylinder with a conical or domed steel roof permanently welded to the top.
And the inherent danger there lies in the empty space inside. As the liquid level goes up and down during transfers, there is always a void space between the liquid surface and the fixed roof.
That void space is where the vapors accumulate.
Right. It's a constantly shifting environment where the vapor-to-air ratio frequently enters the critical explosive range.
So to eliminate that void space, engineers developed a floating roof tank. Instead of a static dome, the roof literally floats directly on the surface of the liquid hydrocarbon.
It acts like a massive steel piston inside a cylinder.
As pumps fill the tank, the liquid pushes the roof up. As it drains, the roof rides the liquid all the way down.
It is a phenomenally elegant solution to a massive thermodynamic problem.
Because the steel roof is resting directly on the liquid, there's virtually zero void space. No trapped air, so no oxygen available to mix with the vapors.
By taking atmospheric oxygen out of the equation, you completely neutralize the explosive potential inside the tank. And because the internal risk is so much lower, NFPA 30 lets you space floating roof tanks slightly closer together.
But whether it's fixed or floating, it's still a massive steel vessel exposed to the weather. The steel heats up under the summer sun, causing the liquid to expand and vaporize. It cools at night, causing vapors to contract. When millions of gallons are pumped in, massive volumes of air must be expelled. When it's pumped out, air must be drawn in, so the immense vacuum forces don't crumple the steel shell like a cheap plastic water bottle.
Which brings us to what Chapter 22 heavily regulates: venting.
The respiratory system of the tank.
Exactly. The code mandates two distinct categories: normal venting, which effortlessly handles daily thermal breathing and fluid transfers, and emergency relief venting, which is designed for catastrophic thermal events.
Emergency venting is basically the macroscopic, heavy industry equivalent of the melting plastic drum we just talked about.
It really is.
Consider the scenario. An external fire breaks out in the containment dike surrounding a 50,000-gallon tank. Flames lick the outer steel shell. Tremendous thermal energy transfers through the steel, and thousands of gallons of liquid inside begin to rapidly boil and vaporize simultaneously.
If that astronomical volume of expanding vapor cannot escape, the entire tank will catastrophically rupture.
A BLEV on a municipal scale.
Precisely. So NFPA 30 strictly dictates that emergency relief venting must be precisely sized to prevent the internal pressure from exceeding a gauge pressure of just 2.5 psi, or 20% of the tank's calculated bursting pressure, during a fully engulfing fire.
2.5 psi. Again, it sounds so delicate for a structure built from thousands of tons of welded steel.
But a flat-bottomed AST is fundamentally not a pressure vessel. It is engineered to securely contain the static downward weight of the liquid column. It is highly vulnerable to outward pneumatic pressure.
If the emergency vents are overwhelmed and pressure spikes, the steel will yield at its weakest structural point.
Which leads to another brilliant integration of engineered failure.
Oh, the frangible roof design.
Yes. The code extensively references tanks built with a weak roof-to-shell seam.
To a layman, intentionally designing a weak weld on a critical infrastructure project sounds completely absurd.
It does, but it's an engineered safety valve. The weld connecting the roof to the vertical side shell is intentionally calculated to be structurally weaker than the massive welds connecting the side shell to the heavy bottom plate resting on the foundation.
Because if the internal pressure outpaces the venting and the tank is inevitably going to fail, you absolutely dictate where it fails.
Exactly.
If the bottom seam failed, the pressure would lift the entire cylindrical shell off its foundation, releasing a 50,000-gallon tidal wave of burning fuel that would obliterate the dikes and sweep across the facility.
But by engineering a weak roof seam, the failure is directed vertically. The internal pressure shears the roof clean off, venting the massive explosion straight upward into the sky, safely away from personnel and surrounding infrastructure.
While the heavy bottom shell stays intact, keeping the liquid fuel safely contained within its original footprint.
It's the exact same philosophy as the melting plastic IBC. Direct the energy where it does the least amount of harm.
And managing that vented energy requires strict oversight too. Chapter 27 governs piping and venting routing. If you have an emergency vent rapidly expelling highly volatile vapors to save the tank, where do those vapors go?
The code is explicit. Vents must discharge vertically upward or horizontally away from adjacent structures. You cannot route vapor streams where they might pool under structural
And
eaves.
critically, they have to be situated far away from any building HVAC intakes. If an adjacent office building's ventilation sucks in the massive vapor plume expelled by an emergency tank vent.
You've just pumped a highly explosive, pre-mixed fuel-air payload directly into an occupied space.
The routing of the invisible vapor is as critical as the welding of the steel tank.
Absolutely.
We have journeyed from the microscopic mechanics of the closed-cup flashpoint test, navigated the rigorous structural requirements of indoor storage and automated foam suppression, analyzed the violent pressure thresholds of steel drums, and scaled all the way up to the intentional architectural weaknesses of a massive refinery tank.
It's all intricately mathematically connected.
To bring this all together for you listening, whether you are a seasoned engineer or a safety officer stepping into a new role, we have distilled this deep dive into 3 actionable, highly critical operational principles based directly on the NFPA 30 text.
Principle number 1 is foundational. Never, under any circumstance, assume the hazard classification of a liquid based on its generic commercial name.
This is a subtle trap that frequently catches junior planners, isn't it?
Constantly. An operator might say, oh, we're just storing standard cleaning solvent, or it's just a light adhesive. You cannot design a life safety system based on a colloquial label.
Ignitable liquid is a massive umbrella.
It is. As an engineer, you must demand the precise safety data sheet. You must extract the exact closed-cup flashpoint and boiling point. The specific matrix classification, whether it's IA, IB, or IAA, rigidly dictates every subsequent architectural, mechanical, and fire suppression decision.
If you design the ventilation and sprinkler density assuming a Class 2 hazard, but the chemical is actually a Class IB,
Your building is legally non-compliant and inherently lethal the moment operations commence.
Principle number 2, obsess over your container combinations. We spent a lot of time analyzing Chapter 16 and Annex E because the suppression math is unforgiving.
You cannot just implement a generic warehouse sprinkler grid and assume you are protected.
Right, the protection criteria are inextricably linked to the specific vessel holding the liquid. Are they in rigid, non-metallic containers? Composite IBCs? Sealed steel drums? Are they explicitly designated as relieving or non-relieving?
And equally critical is the physical arrangement. Table 16.5.2.1 and the subsequent design matrices shift their density requirements drastically based on whether the containers are stored in multi-level steel racks or simply stacked in solid, palletized piles on the floor.
Because in a high-rack storage configuration, a fire can leap vertically from tier to tier with terrifying speed.
While the horizontal steel shelving physically blocks the overhead ceiling sprinklers from penetrating the lower levels. The code dictates that rack storage often requires extensive in-rack sprinkler networks to supplement the ceiling grid. The container material and the spatial geometry dictate the required suppression density.
Which brings us to the final and perhaps most insidious hazard. Principle number 3. Beware the immense danger of the change of use.
This is a scenario that constantly jeopardizes safe facilities without a single piece of equipment ever malfunctioning.
Let's paint the picture. Imagine an engineer meticulously designs a fully compliant, heavily regulated facility for a tenant whose primary operation involves storing Class IIB liquids, stable products like heavy motor oils.
The inherent volatility is low, so the sprinkler system relies on standard water density, mechanical ventilation is minimal, and the MAQs are highly generous.
Fast forward 10 years. That tenant vacates the property and a new tenant signs a lease. The new tenant manufactures alcohol-based chemical reagents, highly volatile, Class IB and IC liquids.
The physical footprint of the building hasn't changed an inch, but the internal risk profile has just undergone a magnitude shift.
The liquids have completely different thermodynamic behaviors. If the property manager just hands over the keys without engaging an engineer to meticulously reevaluate the existing space against the strict mandates of NFPA 30UF,
the facility instantly transforms into a ticking time bomb. The MAQs for the new Class IB liquids will be egregiously violated on day one.
The standard water sprinklers will be vastly inadequate and potentially catastrophic if the new liquids happen to be non-miscible hydrocarbons.
The ventilation turnover will fail to clear the newly introduced, rapidly accumulating vapor layers. A change in the liquid classification demands a total comprehensive re-engineering of the facility's fire protection strategy.
It is the ultimate invisible threat. The steel columns, the concrete floors, the paint on the walls, it all looks exactly the same. But the underlying physics operating inside that space have fundamentally altered. Defending against those invisible physical laws is the true job of the fire protection engineer.
Precisely. You are not just complying with a book of rules, you are implementing a thermodynamic defense system.
Let's recap the terrain we've covered today. We started by shedding the ambiguous, subjective legacy terms of flammable and combustible, recognizing that universal safety relies on the objective reality of the closed-cup flashpoint.
We use that metric to navigate the rigid mathematical boundaries of maximum allowable quantities.
Discovering how active engineering controls like those highly specialized 18-gauge, double-walled thermal cabinets and dense sprinkler networks allow an operation to scale safely by aggressively managing the ambient heat.
We examine the complex fluid mechanics of suppression, understanding why an expanding foam blanket is absolutely necessary to choke the vapor release of a hydrocarbon fire.
And we confronted the violent reality of pressure thermodynamics, exploring the catastrophic threat of the BLE, and why the smartest engineering decision is often intentionally sacrificing a melting plastic container to avoid a structural detonation.
Finally, we applied those same pressure mechanics to the macroscopic scale of above-ground storage tanks. Seeing how spatial isolation, floating roofs, and intentionally frangible seams are meticulously designed to direct and manage catastrophic energy failure.
Mastering the 2021 edition of NFPA 30 is not an exercise in memorizing endless tables and footnotes. It is about fundamentally grasping the physical behavior of vapor, the immense power of heat transfer, and the unforgiving mechanics of pressure.
It is about engineering a system that gracefully survives its worst possible day.
But as we bring this analysis to a close, we have to look at the horizon. The industrial landscape is not standing still, and the codes that govern it are constantly forced to adapt. We are currently witnessing a massive rapid shift toward novel chemical processes.
Sustainable bioengineered solvents.
Exactly. We have massive logistical supply chains dedicated to advanced energy storage fluids, synthetic aviation fuels, and highly complex proprietary chemical mixtures designed to power green technology.
And this introduces a highly provocative reality for the fire protection industry. Many of these next-generation, highly specialized liquids exhibit deeply unusual burn characteristics.
They do not conform cleanly to the behavioral models of our legacy petroleum products. A complex lithium-ion electrolyte fluid might not neatly align with the hazard assumptions inherent in a 100-year-old flashpoint and boiling point classification matrix.
Which raises an incredible challenge for the structural engineers, the safety officers, and the NFPA committees looking toward the future.
Will the next iteration of the code, the 2024 or 2027 editions, be forced to abandon these straightforward temperature metrics altogether? As our fuels become more complex, are we moving toward a regulatory future where we have to utilize advanced molecular-level risk profiling to truly comprehend how a novel fluid will behave when exposed to extreme thermal stress?
Will the universal Scoville scale of volatility need a fundamental upgrade?
It is an incredibly demanding technical challenge. The physics of fire remain constant, but our fuels are evolving, which means our defensive geometry must evolve with them. Something for you to deeply ponder the next time you are analyzing a facility's storage manifest, tracing the lines on a blueprint, and realizing that the boundary separating order from absolute chaos is meticulously managed by just a few degrees of temperature and a few feet of space. Until next time, keep diving deep.